For example number 2, it's quite similar to example 1. We're dealing with a different particle, but we're still going to deal with wavelength formula. And how you'll notice that, as soon as you see a particle and a wavelength attached to it, you know you need de Broglie's formula at some point. This case, we're going to actually find the potential difference, so we're going to also include a conservation of energy. So it's got some similarities to example 1 with a couple minor differences. An alpha particle has a charge twice the elementary charge off our data sheet. It has a mass 6.65 times 10 to the negative 27 kilograms. It also has a de Broglie wavelength 2.66 times 10 to the negative 13 meters. Do a little bit of thinking on this. Remember, example 1 had a wavelength 10 to the negative 12 for a proton. Again, an alpha particle being a little bit larger, heavier, should have a smaller wavelength. So the proton was negative 12, the alpha particle negative 13, and you can see as mass gets larger and larger and larger, wavelength gets smaller and smaller and smaller. It's one of the reasons why that I can't diffract around something, is because of my mass being so large, my wavelength is so small that when I collide into an object, I behave like a particle and bounce off. Whereas if I was incredibly small, I'd behave more like a wave and bend around it. So with everyday objects, way too small of wavelength, that's why we behave like particles. But when you get to really small objects, electrons, their wavelengths are significantly larger that they actually do have some significance. So what we're going to do is start with the de Broglie formula. Wavelength equals h over mv. Now since we're asked for voltage, voltage is always related to velocity. Alpha particles, all of their energy is considered to be kinetic because their masses are so small. So that kinetic energy then can be converted into potential energy, which we'll do in the second formula. First thing we'll do is find velocity. Velocity equals h over m lambda. If we put these numbers in joules again, 6.63 times 10 to the negative 34 joule seconds divided by 6.65 times 10 to the negative 27 kilograms times 2.66 times 10 to the negative 13 meters, we should find that the velocity of this works out to 3.74 times 10 to the 5 meters per second. And again, I'm rounding. Should be 3.75, I guess, if you go to exact, but I'm going to keep this exact value on my next part of the question anyway. To do the voltage, now we go to conservation of energy. The potential energy that this would have been accelerated through would be equal to all of the kinetic energy it converted into. So if we want to find voltage, it's going to be equal to mv squared divided by 2q. Put those numbers in. 6.65 times 10 to the negative 27 kilograms times the velocity, 3.75 times 10 to the 5 meters per second squared, divided by 2 times the charge. So I'm going to go 2 times 3.20 times 10 to the negative 19 coulombs. If you punch this in, you should get 6.65 to the exponent negative 27 times 3.75 times 10 to the 5 squared. Don't forget about that. divided by 2 times 3.2, the exponent negative 19. You should get a voltage of about 1.46 times 10 to the 3 volts. This means it was accelerated through basically 1,460 volts to get it up to the speed of 3.75 times 10 to the 5, and therefore has a wavelength of 2.66 times 10 to the negative 13. We kind of worked our way backwards in example 2. I gave you the resulting wavelength, you figured out what its speed was, then you had to figure out, to get it to that speed, how much voltage was required.